C'est vrai? Comme ça? Hi everyone, good morning. It's our pleasure to have Sandro Tacchella with us. Sandro did his PhD in Zurich, I believe, and then he was a postdoc at Harvard, at Cambridge in the USA, working on Hubble HST with 3 camera data on early galaxy formation and the rise of bulge and disks in galaxies across cosmic time. And now we move to the very early universe with James Webb data is now part of the NIRCam science GTO team, so guaranteed time team. He was an assistant professor a couple of years ago in Korea, and now is an assistant professor at Kavli Institute of Cosmology in Cambridge in the UK and the Department of Physics at the Cavendish lab. And he's going to tell us about the vigorous growth of early galaxies and recent results with James Webb. Sandro, the floor is yours.
Okay, thank you very much for the kind introduction, and it's an honor to be here today. And yeah, take you to basically some of the deepest images we have taken of the universe to date. So what this shows you here is a small region of the sky in Good South, taken as part of the NIRCam and NIRSpec GTO team survey called JADES, JWST Advanced Deep Extragalactic Survey. And what you see is basically an image of the sky at 1, 2, and 4 micron. Now, of course, the cosmologist in the room says, well, that's great, but of course, this is not really, how far we can look. We can look, of course, much further back in time. And so let's start at the cosmic microwave background, which shows you basically how the universe looked like roughly 400,000 years after the Big Bang. Now, we can build, actually, just based on gravity, use body simulations to actually use this kind of as initial conditions of the universe, and then basically propagate them forward and see how, just how the dark matter fluctuations in the universe are growing. And what you can see here is a prediction from the Millennium simulation showing you how the dark matter is distributed in today's universe at redshift 0. And what you can see is basically a filamentary structure. You can see dark matter halos forming. And, in these very bright regions, you can see basically the centers of galaxy clusters. And so one of the key successes of this model, lambda CDM, so dark energy plus cold dark matter, was that we are able to actually reproduce the large-scale structure of the universe, how galaxies are distributed on a megaparsec scale. Now, there are, of course, many other predictions, but when you think about just a simple scenario for how galaxies are forming and evolving, thinking about this as a backbone is very important, right? You have first, again, this growth of these dark matter fluctuations. So, it's a bottom-up scenario where you have the smaller halos forming first, and they are merging into the larger systems. You have then basically the baryons that see these, overdensities. They are following them, they are cooling, and you're forming stars. Now, what we find is that actually it's very important to have some regulation of their star formation. What I show you here at the bottom left is the number density of objects as a function of stellar mass. Now, when we assume that basically each dark matter halo hosts, the amount of stars as given by the baryon fraction, you would get this red dashed line. And you can see when you compare this with the galaxy stellar mass function, so again, the number density of galaxies is a function of their stellar mass, you can see that, around 10 to the 11 solar masses, these two curves, basically nearly intersect. This means that galaxy formation and star formation is very efficient there, but both at low masses and at higher masses, you need somehow to regulate their growth. And this is basically a third point, right? So galaxy growth, there needs to be some regulation to prevent overcooling. So this is usually associated to feedback from stars and black holes. Now, why is this still a problem today? Why don't we understand this better? Well, the challenge is really thinking about the scales for galaxy. So here I show you again this map of the dark matter, the cosmic web. Again, this is roughly on gigaparsec scale. And when we think about galaxies, right, they're forming in the centers of dark matter halos. that are of the order of megaparsec scale. Galaxies themselves are, a few kiloparsecs. And then when you think about the processes that take place in galaxies, you're having, black holes that are really small-scale phenomena, basically, but have a big impact on larger scales. And then we have star formation, again, taking place on parsec scale. And the challenge is to understand how all these scales, both in space, but also in temporal cells in time, basically are related to each other, because we have a wide range of different physical processes that I highlight here that are just part of them. Thinking about star formation and the feedback, such as supernova explosions, stellar winds, but also the black hole growth and black hole activity and the feedback processes, to basically thinking about hydrodynamical processes of gas cooling on larger scales. And the challenge here is really to understand how these small-scale phenomena link with these large-scale phenomena, but also the large-scale phenomena with these small-scale phenomena, because it matters whether, for example, a galaxy is born in a kind of a cluster-like environment or somewhere in the field or even in a void. Now, so how do we learn about galaxies? Well, the simple recipe, you might say, well, is actually let's just take deep surveys, such as with the Very Large Telescope in Chile or the Hubble Space Telescope, and look at things that are further and further away, right? So we can look further and further back in time. And this is, of course, great. So we can think about how galaxies evolve with cosmic time. But what I want to stress here, then we can do things such as this, right? The cosmic star formation rate density. So this shows you the amount of star formation in a co-moving volume as a function of look-back time, or redshift. And then you can see here, a lot of the data points that we have been collecting over the last 20, 30 years. And you can see that basically we had the recombination epoch, we had the dark ages. Cosmic dawn is the epoch when the very first stars, black holes, and galaxies form. And then we have the epoch of ionization, where the universe went from being neutral to being ionized. And you can see then the cosmic star formation density was kind of ramping up. And we had the cosmic noon epoch, where, around redshift of 2, basically most of the stars in the universe formed. And since then, the cosmic star formation rate density has been decreasing. Now, what I want to highlight is that this is, of course, a great view of the universe, but it doesn't really tell us about how individual galaxies are evolving. Right? As physicists, we are used to think of like, well, we have a prediction, a theory that makes a prediction, and we can test this in a laboratory and see how, usually through time evolution of the system, how it's changing. But for galaxies, it's not that we're observing here the same galaxy as a function of time, right? Here we're looking at how the galaxy population looks as a function of time, and we are at each epoch observe a different set of galaxies. And the challenge really is understanding how these different processes that I was highlighting before relates to basically how galaxies evolve with time through diagrams such as those. So what are some of the key questions that I think are still open today? I think, again, when we think about the very high redshift, the early universe, it's really about understanding how the very first stars and black holes formed and evolved, how these systems also then reionized the universe, how the galaxy is chemically enriched and build up all the elements that we are made up of today. And then, as in the introduction was mentioned, I'm personally very interested also in understanding how the structure of galaxies is evolving, right? How does bulge and disk component galaxies form, and how are they related to the regulation of star formation? So, thinking about very simple galaxy formation models. So again, we have lambda CDM, where you have halos building up from small scales to larger scales. And a very successful simple model was what we call the regulator model, where you basically say that the star formation rate in a galaxy can be related to the available fuel of the galaxy, right? So you have some kind of accretion onto the galaxy, given here via, for example, linking this to the dark matter accretion rate. And so you can come up with this very simple equation where you say that the star formation rate of a galaxy, if in a given dark matter halo of some mass at a given redshift, is some star formation efficiency times the gas accretion rate. And here the gas accretion rate is just the dark matter accretion rate times the baryon fraction. And what you can see here is that because we want to make this model as simple as possible, we assume that the star formation efficiency just depends on halo mass and not on epoch, right? No redshift dependence, which is, of course, a very strong assumption. So now we can, of course, ask, well, where do we get the star formation efficiency from? Well, we can use, for example, the stellar mass function or a UV luminosity function to calibrate this model. And so this is what we would call an empirical model. You basically motivate this model from direct observations, and you're not doing kind of an ab initio physical model. But if you would do so, for example, through numerical simulation, you might then say, well, this is related, for example, to stellar feedback and black hole feedback. So again, this curve here shows you the star formation efficiency. So how efficiently are you converting the accreted gas into stars? And you can see it peaks around 10 to the 11 solar masses. And again, this is consistent with before, where you basically have the idea that, yes, there is some efficient conversion around this halo mass, but before and after, so above and below this threshold, you have some kind of regulation. So again, this model has been calibrated now specifically at redshift 4 through the UV luminosity function. Another question is, of course, how well are you doing? Well, when we focus now, especially at high redshifts, right? So this is basically in the first giga year of cosmic time. You can see here that we have calibrated the model at redshift 4. And now going back in time, you can see that when we go to higher redshift, this model makes a very strong prediction in the sense that it decreases very drastically, right? You have basically 5 orders of magnitude in a decrease of the cosmic star formation rate density. And from redshift 4 to redshift 14, basically. And this is consistent with what we had pre-JWST, right? So these are data from different surveys that people have been using, the Hubble Space Telescope from. And it's interesting because this was basically consistent with having no efficiency, no evolution in the cosmic star formation efficiency, right? I said this model is just driven by dark matter halos assembly, basically, and there is no change in the star formation efficiency. So what does this specifically mean? So again, we have the star formation efficiency. And what I show you now is basically how the dark matter halo mass function, so the number densities of dark matter halos, is building up with cosmic time from redshift 10 to redshift 4. So you can see the number density shown on the right. And the key thing here to see is that indeed, from redshift 10 to redshift 4, you can see how the halo mass function is moving into this regime where you now are able to host galaxies that are having efficient star formation. And that's why, together with the increased dark matter accretion rates, you have this very stark increase in the cosmic star formation rate density at early times. Now, there are actually other models, and of course, with Joel Silk here, right? There's one of the models that actually, changes some of this, and you can see that, there were other models that made a prediction with much higher cosmic star formation rate densities at early times. And so I think that's why actually it's very interesting to think about how many, the galaxies there are in the early universe to understand how efficient this star formation really was, because you can see that all those models converge, not too surprisingly, at lower redshift and are consistent with the observations. Yeah. Yes. Sorry, say again? What the light purple inside? That is basically some of when it comes to the calibration of the model, basically the uncertainty that is propagated from the UV luminosity function. Okay, that's at the high mass end, yes. So how do we find these high redshift galaxies? When we think about taking these deep images, one of the key ways to identify those objects is through the dropout technique. So the idea is that the high neutral fraction in the intergalactic medium absorbs all photons that are shortward from the redshifted Lyman alpha line. And so the idea is when you look at this, is basically when you have a galaxy around the redshift 11, as shown here, GNZ11, an object I will be talking more about in a few slides. You can see that the object has not been detected basically up to about 1.2 micron. And then, around 1.4 micron, it starts being detected and it's really visible then at 1.6 micron. And so with Hubble, this is basically all data from Hubble up to 1.6 micron. You can see that when we have objects that are beyond redshift 10, they would have been detected only in 1 or 1.5 bands. And then we relied on either ground-based photometry, as here shown with the K-band at 2 micron, or IRAC with Spitzer at even longer wavelengths. But the challenge there was, of course, spatial resolution, as you can see here, right? So at 4.5 micron before JWST, we were suffering basically from rather low sensitivity, but also low spatial resolution. And so that's why we built this telescope here, a $10 billion telescope that went into space, the James Webb Space Telescope. And I'm sure you have heard a lot about it, so I don't want to talk too much about it. But there are 4 key science instruments: NIRCam, NIRSpec, MIRI, and NIRIS. And I myself am part of the NIRCam science team that delivered the NIRCam instrument, and I myself worked mostly on the software side on that instrument. Now I think The crucial part is, again, the larger mirror, right? So we have, we can have more collecting area, we have more sensitivity. But then again, you can also go much further into the infrared, which is crucially important if you want to characterize and study the very first galaxies. And the additional component, of course, is spectroscopy. So it's really kind of the first high-resolution spectrograph in space. And you have to imagine that what we had previously with Hubble and with a GRISM going, with near spec now, and in comparison with ground-based facility, the increase in sensitivity at fixed resolution is roughly a factor of 3,000, which means that you're going from Galileo's telescope to the VLT, right? So the discovery space is really, really large. So I just want to briefly mention the JADE survey. Again, this stands for JWST, Advanced Deep Extragalactic Survey. And this is really stemming from both combining near spec and near cam. The idea is that you need photometry, you need images to select the most interesting objects in the sky, but then you need spectroscopy to really characterize them. And so this is the motivation to basically come together, two different teams basically, and build this survey. And it's over 800 hours in pure and parallel, and we have additional programs that I will explain to you afterwards. So we have over 1,000 observation hours on this telescope, focusing particularly at good south and good north. And the main science driver was really understanding the formation of the first galaxies and then how they evolved to basically form the universe we observe today. Again, there is a large team. There are also, actually several team members here in Paris, including Stéphane Charlot. All of those people have, of course, contributed in various steps in this survey. Now, I want to highlight that actually a lot of the data is already public. We had our third data release in April this year. You can either download this directly from us or from our website that is shown above. And we have several data release papers. Again, the key thing to see up there on the top right is, for example, the point source sensitivity. And you can think of that large fraction of this survey, actually the red part on the upper left here, is as deep as what Hubble was able to deliver in the Hubble ultra deep field, but to much longer wavelengths and to much larger areas. And you might say, Sandro, like, you are on the near cam side. Why did you choose the mosaic pattern so wildly? And the motivation for that was actually that we always wanted to make sure we do spectroscopy on the deep areas as well. So that's why when you look at this, it looks a bit like a mess. Yeah. Okay, just to put you very quickly into the context of some other surveys that are going on. There is Cosmos Web, that is a much larger survey, but only has 4 filters. There is Primer, there is Sears, WDeep, and several other surveys. Again, you can see with the darkness of the color depth. And so JADE is really this unique parameter space where we go actually very deep in most filters. And I think we also have the most extensive spectroscopic follow-up. As you will see, that is very crucial to not just identify the high redshift objects, but also to characterize their distances in detail and their properties. So I just want to show you a bit of the data. Again, when we started putting together these mosaics, and again, you can look online and we have even a viewer and you can scroll around, to make sure that you can appreciate the full depth of these images. I'm zooming here on a small region of the sky. So here is a scale of 3 arc seconds, just to give you a bit of a scale. Again, this is at 1, 2, and 4 micron. And it's just beautiful. Like the galaxies actually come in a wide range of different shapes, colors, and it's actually quite difficult sometimes to then run source detection and photometry on these systems, as you can imagine, because many of the systems are actually, overlapping, right? We go very deep, and so we have a lot of overlapping isofolds. There's a lot of color information, of course, that we would like to include more in the future as well. And so this is something that we are still actively working on. Now, this is showing you a nice object. This is a galaxy that we have kind of known, but it was much more difficult to see. This is HST ACS I-band. And you can see that there was something there in the foreground. And now this object is clearly visible here. And it's actually a grand design spiral galaxy at redshift of 2. Right? So this object here that looks to us like, oh, this might be not too far away, is actually already at redshift 2. And we have to kind of recalibrate the eyes that we trained on Hubble images, saying like, oh, this is a redshift 2 object, redshift 1 object, redshift 0.5 object. I needed to really recalibrate and see that most of these things that I thought they were at redshift 0.5 are actually at redshift of 2. So the structures that we see are very rich. This shows you a direct comparison to the deepest image we had before. This is the Hubble HST H-band, it was a 1.6 micron image in the Hubble ultra deep field. And this shows you the same image, but basically with, like nearly only a 20th of the exposure time, right? So you can see that, at much shorter exposure times at the same wavelength, we are starting to see more substructure in the galaxies, right? So even for the people like me who like the foreground galaxies and study the bulges, the disks, and the clumps in the galaxies, you can clearly see that there's much more substructure there. But also when we look at the background, it's much more homogeneous. You can start seeing smaller objects appearing basically in the background. And again, what I want to stress here is actually the spectroscopic component. Again, images are great, and you can do already a lot of science with them, but you need spectroscopy to really then characterize these systems. You can see up is a prism spectrum. So again, this is basically showing you the observed wavelength from about 0.6 or 0.7 micron up to 5 micron. You can really see a wide range of different emission lines, tracing the chemical pattern, for example, or the star formation rate when we think about the Balmer lines. And then important is that we not only observe them with prism, which is kind of the low resolution part of the spectrum, but we also did high resolution follow-up, which then allows us actually to study the kinematics of the gas. So here, for example, shows you specifically on oxygen 3 line, you can start seeing basically broad components under the narrow components, which is important, for example, to trace outflows in galaxies. Okay, so I will talk a bit more about the morphology first before moving into the very highest redshift regime, keeping always an eye on time as well. So one thing when you think about the formation of galaxies and their morphologies is that over the last few years, in particular with Hubble, but also with ground-based IFU observations such as OSIRIS or SYNFONY, we have been able to characterize the structure of galaxies up to about redshift 2 or 3, right? Thanks to probing the rest frame optical. So this shows you some of the work I've been doing in my PhD and early postdoc, which you basically can see the Hubble images, B, I, and H band, which covers the rest frame UV and rest frame optical light. Then with SYNFONY, we were able to map out DH alpha. So you can see basically where the very young ionized gas is. And then you see basically the kinematics based on the blue and red shifting of DH alpha emission line. And so it was clear that already at redshift 2, we are seeing rather mature galaxies with high central densities that have, something like a disk-like component that is usually, much thicker. And so the question is, what do you learn from JWST? And here I want to specifically just focus on one system. There's of course much more to talk about, but I just want to highlight here some work that I've been doing with a PhD student in Cambridge, where we have been looking at this object up there to the right, that is at redshift 7.4. So this is spectroscopically confirmed. You can see here the near spec spectrum that shows no indication for an HEN. It's just pure star formation. And what we find is that even though this galaxy is very compact, when we look at the spatially extent of this galaxy in different bands and look at the color gradient across the system, we can clearly see that there are color differences as a function of radius, and they are also different for different colors. And so one you can see here is, for example, that there seems to be an excess in the 410M. So this is a medium band at 4 micron that increases with the spatial extent, with the radius in the galaxy. And so in order to model this, again, because these galaxies actually are very compact, we needed to develop a new tool. And we have been doing this actually over several years, in particular during my postdoc time at Harvard with Ben Johnson, who is a senior scientist at Harvard. We have been trying to figure out how can we actually improve the morphological measurements. Because when we work on mosaics, right, we have one pixel representation of the data. So we have, of course, many exposures that we take with the James Webb Space Telescope. They're usually what we call dithered. They are slightly moved from each other. But then when we combine the images, we put them down onto a fixed grid. And that's usually slightly higher resolution than what we have is the initial pixel sizes, by some fraction. But when we model the data, we usually work on the mosaics because that's where the signal to noise is high, and this is what we do. And what we try to do now with ForceFo, which is this new code, is actually use the individual exposure. So we still try to model the galaxies with a Sersic model or several Sersic model, but we are doing this we forward model basically all the individual exposures. And this helps us to basically get a representation of the galaxy that is sub-pixel scale, even sub-pixel scale from the mosaic. And so we have been now using this to model this galaxy. And what we do is like basically kind of a core, a central component, and an extended component decomposition. And when we do this, we find that the core, has has a surface index of about 2, is very compact, only about 80 parsecs. And then the disk is more extended, surface index of 1, but we fix this. And then we have an effective radius about 400 parsecs. And so we have this core disk decomposition, and then we have a clump in the outskirts as shown there on the top right. And what we do is basically we try to model the SED of those subcomponents individually. Okay, so we do this at all bands simultaneously. And so we can get what we call like an SED, like a flux as a function of wavelength for these two different components. And what you can see then is that the disk is significantly younger, much more star forming, where the bulge or the core is much older. So when we do this, we can see that here on the left is the stellar mass surface density profile. Again, the core is dominating a large fraction of that. But when we look at the star formation rate surface density profile, you can see the disk, the blue, is dominating actually a large fraction of that. And so what we can do then is infer the specific star formation rate, right? So the star formation rate divided by the stellar mass is a function of radius. And the black dashed line shows you the combined profile of this. And you can see that in the central core, specific star formation rate is about 10 to the minus 8.5, which implies that basically the galaxy is doubling its stellar mass roughly every 200 million years. And in the outskirts, we are more towards 10 to the minus 7, which means that you're doubling your mass roughly every 10 million years. And so this shows you that basically we have already quite a massive central concentration of stellar mass in the center. And most of the star formation is actually more extended and leads to actually growth in the outskirts. And you can see that the half mass radius, as indicated by this dashed line, basically is of the order about 160 or 200 parsecs, and most of the star formation is actually taking place in the outskirts. And this is interesting, right? Because of course you want to then understand how does such a galaxy, such a very compact system, connect to these galaxies that we observe at slightly later epoch. Now, with the very drastic assumption where we say that this galaxy keeps forming its stars as it does at the moment, we see that the galaxy would evolve in mass and size, basically from this very, region at the bottom left to the upper right, right? So you're basically growing inside out, and you're really, without any specific assumptions, actually quite naturally arrive at the size-mass relation of quiescent galaxies at redshift of 2. If we take now the stellar mass of this system, right, which is a few times 10 to the 8, so it's not very massive, but compare it to the mass profiles of local elliptical galaxies, you can see this there at the bottom right. Let me see if this works, right? So here, so all these curves here are basically massive ellipticals in the local universe, and this orange line shows our 10 to the 8 solar mass galaxy at redshift 7. And you can see that actually in the central core of the galaxy, we have a very comparable stellar mass density, right? So a few times 10 to the 10 solar masses per kiloparsec squared. But we are missing, of course, a lot of stellar mass in the outskirts. Again, this galaxy is about a factor of 1,000 lower in stellar mass, but the central density is already very comparable. And so this is consistent with this picture that you might still grow very actively, inside out, until you what we call quench or suppress the star formation in the galaxy about 10 billion years ago or a redshift 2. And then you still need to grow inside out through, for example, minor mergers in the outskirts of such a system. And this shows you what we can nowadays do with the James Webb Space Telescope using both spectroscopy and the imaging data. So now I want to move on to actually think a bit more about the regulation of star formation. Okay. So when we think about, star formation in galaxies, I showed you this very simple picture where we have the gas coming into a galaxy. There is some, recycling of gas, right? So the gas gets, into stars, and the stars produce outflow. So there is basically a rather, what we would say, smooth accretion version of the universe, right? So you're just feeding the galaxy constantly with gas, and this converts into stars. And this is the star formation rate you observe. Now, we can think of this also in a more, variable approach, right? Because obviously the accretion might not be constant or smooth all the time, but it might come in fluctuations. You can think of the extreme case where you think about mergers, right? Obviously there, you can imagine that there's a lot of gas coming in one instant, and then, maybe you wait 200 or 300 million years, and the rate of gas accretion is much lower. So you have some variation in the accretion rates with time. But you can also think about the star formation process itself, right? We have processes in galaxies, for example, spiral arms, bars that drive star formation on a certain time scale. Or when you think about dwarf galaxies, you might really see the formation of individual giant molecular clouds and disruption of those. And so we have been thinking about this in the term of this regulator model and extending it basically to understand the time variability. And so this shows you basically what we call the power spectrum of star formation rate fluctuations. So we basically try to understand how correlated is the star formation over different timescales. And here we have been building a model where you basically say that the star formation is sustained through GMCs. So you have still the accretion onto the galaxy, but then you're sampling a giant molecular cloud mass function to have some prescription for star formation that is in situ in the galaxy. And so then there are two ways to think about star formation variability in such a simple toy model. One is basically making the inflow variable, right? You're kind of randomly feeding the galaxy with gas. And then there is the other side, where is basically the sampling of giant molecular clouds. And again, in like Milky Way systems, you might say, well, there are so many GMCs forming and disrupting, you don't see that. But when you think about the dwarf galaxy, you might see the formation and disruption of individual clouds. And again, this is what we call like a power spectrum. So you can think that, on long time scales, you're really dominated by the inflow physics and the regulation of star formation. And then you have the star formation process that adds additional power on shorter time scales. Yes. Yeah, so basically you have, in this model, you can imagine that you have some amount of gas, right, that is coming in. You have a gas reservoir. And now the question is, how do you convert this gas into stars? Typically, we do this via a simple prescription of a depletion time. And you just say like some fraction of this gas gets converted into stars. What we do here is to say, well, there is, basically a giant molecular cloud mass function. So you have a distribution of different clouds, and they have certain, lifetimes as well. And then you sample this basically probabilistically. So how does this look? Okay, so again, this is pure, on a toy model side, where you can say, well, I have a rough idea of what the gas fraction in the system is, and then, you're assuming something about the giant molecular cloud mass function. And so you can see here are four, rather different galaxy regimes. So on the top left, you see dwarf galaxies. Top right is a Milky Way galaxy, cosmic noon galaxies, and high-redshift galaxies. And we just put in numbers that we, think are reasonable, for example, for the gas fraction of those systems. And this is then what the model would predict. And you can see that what this shows is basically a distance from the main sequence, or the star formation rate as a function of time. And you can see that the variabilities are very, very different. Okay. And they all reproduce maybe a similar scatter in the star formation, but it's slightly different. And it's different depending on the time scale you are actually observing the scatter from. So you can imagine that if you look at the dwarf galaxy, where the star formation go up and down very, very quickly, and you have two different star formation indicators, for example, one that is H alpha, which means you're tracing very young stars, you can see a wide range of different star formation rates. But if you lose something like UV plus infrared that traces longer time scales, for example, 100 million years, you're averaging over a longer time scales, and you can see less variation. And this is shown here. This shows you the scatter in these star formation rates as a function of the averaging time scale. And you can see now that at short time scales in the dwarf regime, in the blue line, you can see there's a lot of scatter. But when you go to longer time scales, you're averaging over individual bursts, and you see something that is more continuous. And that's why you have this decrease in the scatter as a function of the averaging time scale. And you can see this lesser degree, for example, when you look at the purple line, the Milky Way systems. The Milky Way systems, they vary their star formation rates as well, but they do this on much longer time scales. And so there, the H alpha and the UV delivers very similar estimates of the star formation rate in the galaxy. And that's why the scatter is roughly constant as a function of the averaging time scale. And so you see this can be used to, for example, go beyond just thinking of star formation as individual points in these diagrams, but think about how do actually star formation rates in galaxies vary. Okay, so what can we learn about high redshifts, right? So because this is something that is, of course, very interesting to us, how quickly do actually galaxies vary their star formation rates? And one direct implication for these variations is, of course, what we learn from the chemical enrichment and how bursty these star formations are. At low redshift, so from redshift 0 to 3, there have been many measurements of the metallicities in the gas phase metallicities in galaxies. And it has been shown that there is what we call the fundamental metallicity relation. So there is basically equilibrium between the gas inflow, the star formation rate, and then the outflows again. And you can come up with a very simple prescription to basically estimate what the gas phase metallicity is as a function of star formation rate, stellar mass, and epoch. And you can see that all of those data was basically in agreement where you say that, oh, there is this equilibrium of self-regulation. When we go to higher redshift, and these are just 3 data points because this was like the very first data we obtained from SMEX, from the ERO data, early release science observations. You can see that those data points were all over the place, which meant that somehow for a given star formation rate and a given stellar mass, those galaxies had very widely different metallicities. And the question is why? What's going on? And you might say, well, 3 data points, can be just scatter. But we have been redoing this last year as well, towards the end of last year, with already 100 objects. And what you can see is basically there's a lot of scatter, which is very interesting to understand. I will talk more about this now. But there's also seems to be a departure from this relation. And this means somehow that the metallicities are different than what you would expect given the star formation rates and the stellar mass of those systems. So what's going on? So why are these galaxies basically not synchronizing their star formation rate with their metallicities? And the answer to this, focusing specifically on these galaxies, is kind of in detail. We have to basically combine both imaging and spectroscopy. And what I show you here is a careful SED modeling. So this is showing you the spectral energy distribution of galaxies, and then below you can see different emission lines. So we try model all of this self-consistently with a Bayesian SED fitting called Prospector, and I'm happy to talk more about the details there. But the idea is that you're forward modeling all this data to estimate what are the properties when it comes to the stellar populations for these galaxies. Okay, I think I'm skipping this. So the key thing here is that actually all of those galaxies are going through a burst of star formation. Okay, so you can see here the star formation rate, so the amount of new stars that are forming as a function of look-back time. And you can see that all of those 3 galaxies that are actually having had rather low levels of star formation, but now are all going through a burst. Okay, so it's interesting, right? They're all kind of similar in mass. They're all around 10 to the 8, up to maybe, even still below 10 to the 9, but they're all of the order of about 10 to the 8 solar masses, but they're all going through a burst. So why do they have all very different metallicities, right? So when you look at the gas phase metallicities of these systems, you can see that they're spanning basically nearly an order of magnitude. So the answer to this is actually when we look into the morphology. So you can see this already here, that these 2 systems that have a rather high metallicity, a gas phase metallicity, they are actually much more extended. And they are probably undergoing a burst of star formation because they have some kind of interaction. You can see that they have several multiple clumps there that are very close to the system, right? On the other hand, the galaxy that is very compact, the most compact system actually, has a much lower gas phase metallicity. And so the idea is now that it's maybe the case that we have in this system where we have a high burst of star formation that is driven by different physical processes. In these 2 cases with the higher gas phase metallicities, we are undergoing some interaction, which brings in gas, but it's already pre-enriched. On the bottom right, we have a system where we are undergoing a starburst, so a burst of star formation, because we have fresh gas accretion, basically pristine gas. And what are the implications of this? Well, there are for sure a lot of systems that are very bursty, and you can see this when you look at this analysis, showing you basically a mass-complete sample at a redshift of about 6 to 8 now, so probing the cosmic epoch of ionization. And you can see that when we look at the ratio of the star formation rate averaged over 10 over 100 million years as a function of stellar mass, you can see that it is increasing towards low masses. So there are many more galaxies at lower masses that are basically having an increase in their star formation history. And when we compute now, for example, what the implications are for the number of ionizing photons that are produced by those stars, is actually that we produce enough ionizing photons to re-ionize the universe with all the observed galaxies. So we don't need to invoke, even further down the luminosity function or the stellar mass limit. Basically, the galaxies you're observing are enough to re-ionize the universe. So now the question, of course, is, okay, so we observe these galaxies undergoing a burst of star formation. Are all galaxies bursty? And I think this was a very interesting discovery that we observe galaxies that are actually low in stellar mass, 10 to the 9 solar masses, that are at redshift of 7. So this is a redshift 7.3 object that have basically no emission lines. Okay, do you see this here, the spectrum? You can actually see there are no emission lines. You might say, well, this is because they have no gas, right? The ionizing photons just escape the galaxy. But you can also see, and this speaks against that, is actually the strong break around 4,000 angstrom, which indicates there are actually slightly older stellar population present. And so what we think happened in this galaxy is that this galaxy, because it's still young, underwent a burst of star formation, maybe about 50 to 100 million years ago, and then had a decreasing star formation history of the galaxy. And again, this is consistent with the idea that we have some galaxies really going into a starburst, but then they somehow self-regulate and go down again. And this is basically a galaxy that is probing this epoch. And they are much harder to find, right? So the galaxies that you're observing here that are going through the burst are, of course, much easier to detect because at fixed stellar mass, they're much brighter. But those systems that are basically decreasing their star formation rates are fainter at fixed stellar mass and therefore are much more difficult to detect. So what's the idea when we think about, okay, I'm from the theoretical side. And again, these things are not unexpected. Here I'll show you a range of different models. Again, this is the TNG 50 and 100 model. Then the empirical halo model that I showed you at the beginning of the talk. First light simulation, and then the VILA, which is a cosmological zoom-in simulation. And what is shown here is, again, the variation in star formation from the main sequence, from the star-forming main sequence. Basically, imagine this is just the amount of star formation as a function of stellar mass. And you can see that for all those simulations we have, as always some population at low masses, around 10 to the 7, 10 to the 8, up to 10 to the 9 solar masses, that are well below the star-forming main sequence. So these galaxies have really low star formation rates. And the causes actually are quite wide-ranging. It's not just one simple cause, but many of them have been undergoing some kind of close interaction, which led to a higher star formation rate. So they were kind of at the upper envelope of the main sequence. But then stellar feedback, both radiation pressure, winds, and sometimes even supernova contribute to basically, the push out of gas and then the lack of gas accretion onto the system. They both together then leads to a suppression of the star formation rate. And these things are not what we would call quenching their star formation as in the massive end, right, where we observe the formation of massive ellipticals. But those systems are the ones that are only temporarily quiescent. So that's what we call mini quenching. They're only quenching or suppressing their star formation for a few tens of millions of years. You can see this here. Again, models make different predictions, but we are talking here of maybe 20 to 30 to 40 million year timescales where these galaxies are not forming any more stars. And again, this is not a phase that is very easy to observe because these objects are quite rare. But they are a natural occurrence, they're a natural product of having bursty star formation. So now let me move on in the last 5 to 10 minutes into the regime of really the first galaxies. So the first spectroscopically confirmed galaxies with JWST were actually these 4 objects. So this is work we have been publishing last year. You can see the bottom 2 galaxies have been high-redshift galaxy candidates with Hubble. And the 2 upper ones have been newly discovered in our NIRCam imaging and then spectroscopically followed up. And I'll show you here the spectra. So these are the spectra, and you might say, well, they look noisy, and they're noisy. These objects are actually very faint. And the main key features that we use to measure their spectroscopic redshift is actually the drop from the Lyman alpha line, right? So the Lyman break, basically. And you can see that all of those have a clear break, and together, with the photometry, this all aligns and puts them basically at the redshifts of 10 to up to redshift 13. So we don't find emission lines in those systems, and this is partially because the signal to noise of the data is quite low, but also because we think that these galaxies have rather low metallicity and therefore not very strong emission lines, in the UV, such as C3 or C4. But thanks to those distances now, we can actually estimate their properties in much more detail. And I'll show you here just some of the key numbers that you can take away. Redshifts, the stellar mass around 10 to the 8, 10 to the 9 solar masses. The star formation rates we find for these systems is about 1 to 2 solar masses per year. So this sounds, similar to the Milky Way, and you might say, well, this doesn't sound like a really vigorous growth. But actually, when you compare this to the stellar mass, this still means that these galaxies double their mass roughly every few tens of millions of years. So they're still growing actually very rapidly. You can see this from the images. They are very compact, and we infer sizes of the order about 50 to 160 parsecs. So again, this means that the star formation at surface densities are very, very high, right? Tens up to about 200 solar masses per year per kiloparsec squared. So something much more in the Euler regime. And again, such galaxies are actually quite consistent with lambda CDM. So this is not something that is unexpected, I would say. An object that was actually much more interesting when it comes to thinking about being, basically very bright beyond what you would have expected, is GNZ11. This is an object actually that has been with us for many years, and it had a grism redshift from Pascal Earth's work with Hubble, and it put it basically around redshift 11, but you can see here the absolute UV magnitude is about -22, which puts it really far off, right, to the top right. So this galaxy is very bright given its, redshift, given its, time. And the question is why? And so we had this observed last year. So last year we put together out two papers, one focusing on the spectrum and the other one on the photometry. And well, the spectrum, of course, is astonishing now, right? We see suddenly many of those emission lines that we are actually looking for. And you can now measure the redshift, not just from the Lyman break, but actually from all these emission lines. And we have a spectroscopic redshift of 10.6. You might say, well, what can you do now on the photometry? It's pretty boring, right? But actually, when you look at the neighboring area of this galaxy, you can see that there are actually many other objects that have a similar redshift. And these are only photometric candidates to date, but we have about 9 galaxies kind of in a 5 co-moving megaparsec area around this system. And so again, this would make sense because you would expect that these galaxies are highly clustered and are hosted probably by very massive dark matter halos. So I want to skip some slides maybe, or I'll go just very quickly over this because I want to highlight some other results we are putting together at the moment. But we have been quite carefully modeling the morphology of this system, and we have trying to understand basically what powers this luminosity of this system, right? Why is GNZ11 so bright? And well, you can actually describe it quite well, both the central point source and the extended component in the galaxy, with simple SED models where you just say that the point source in the center is kind of like a nuclear starburst, either forming globular clusters or a bulge or a core. So that actually works pretty well. However, Roberto Malina has been looking into this system and specifically looking at the spectrum and finding that several spectral features, including the C4, has a P-Cygni-like feature, and the densities that are implied by the permitted lines, all of this indicates that actually this galaxy probably hosts an HEN. And so we have the extended component in the galaxy that is really the galaxy, but then the point source in the center that dominates the UV luminosity is actually an HEN, an active accreting black hole. And when we use magnesium line as well as the N4 line, we can infer a black hole mass of the order about 10 to the 6, so about a million solar masses. And so again, this is showing there at the top right, showing that basically this black hole connects very naturally different black hole seed formation mechanisms to what we see with the quasars at lower redshift. So this is very interesting. Now, when you compare this black hole, but also other black holes that have been discovered in the, with JWST, is actually that this black hole is quite massive given its stellar mass. You can see this at the bottom right here. You can see that most of the black holes and the galaxies we have detected with JWST lie above the local black hole stellar mass relation, which is interesting, right? But it's also consistent with this very core that I showed you, at the morphology part of my talk, that basically in this early universe, it seems we have very compact formation of stars and black holes that is very efficient at high redshift. So we have both the cores and these high central densities, but also the black holes forming very efficiently in the early universe to basically produce objects that are above this relation that we observe at lower redshift. Okay, HENs are prevalent. I'm happy to talk more about this. So one thing that I want to just highlight, I think in the last 2 minutes, and I'm moving over these slides, but I'm happy to talk more about this, is that, there is the question whether there are two actually challenges that have been highlighted in the literature, I think most, when it comes to thinking about whether this, efficient star formation is something that we have expected, in particular related to breaking lambda CDM. So the first one is that we have too many massive galaxies at redshifts of 6 and above. And the other issue is actually whether these galaxies form too early. When we think about the masses, I would say that there are actually large uncertainties because even in the work by Labbe, for example, many of these systems have not been confirmed at the right redshift. They were at lower redshift. So one of the key things is actually to measure first the distances. The other thing is actually the HEN contribution. GNZ11 is one of these good examples where you can say that part of the luminosity, even though the major part, comes out from the HEN accretion disk and not powered by stars. And therefore, anything that you learn about the stellar mass might be biased. I also showed to you that galaxies have very bursty star formation. Again, this leads to biases when we estimate stellar masses, because when a galaxy undergoes a burst of star formation, these stars actually dominate the SED, and everything that is older and really makes up the mass is actually very, very difficult to measure. And so this is something that is, this outshining effect is very important to consider and something that is limiting currently what we can learn about the stellar masses of those systems. When you think about too many bright objects, this is something that has been there, but has been, when you think about too many bright objects, usually we compare to these models that I explained to you at the beginning, where we have this smooth accretion. If you now start thinking about, well, maybe objects are very bursty, right? So maybe they have very short durations where they have really bright UV luminosities. You can model this quite naturally in such a model because the idea that when you go to high redshift, what happens is that the halo mass function is very steep. So if you do, if you have some additional scatter at the low mass end, those systems can scatter up and actually dominate the luminosity function. And so this is something we have been looking into in such models, and you can actually come away with not having to induce any kind of breaking with lambda CDM to explain why there are so many bright objects. So again, here we are. So this is currently the object that I showed you. So there's GNZ11. There is another one from the glass team that has kind of similar properties to GNZ11. Then there are the 4 objects that are fainter that I showed you before. And now I want to just highlight to you that we also want to go beyond redshift 12. And so what we have been doing is actually a follow-up of JADES, the JADES origins field, which uses medium bands to really probe the Lyman break, around the redshift of 14. And so we have put together last year this paper where we have, found these high redshift galaxy candidates, many of them around redshift 12, 13, and 14. And the challenge here was actually thinking about, some of these galaxies. In particular, I want to highlight today probably this galaxy up here on the top right, which is this redshift 14 galaxy, which was a high redshift galaxy candidate, but it was very bright. And including this galaxy or not made a huge difference in actually when we infer the cosmic star formation rate density. This is showing you the cosmic star formation rate density as a function of redshift. Including this object or not leads to this large difference. And so the spectroscopic follow-up was very important. And this is basically what we have been doing now. So what I show you here is a spectroscopic follow-up of those 2 objects that have been there as photometric candidates. And now they have been confirmed to be at redshift 14, basically. So in particular, this object up here to the right, this is a system now that has a spectroscopic redshift of 14.3. So only about 280 years after the Big Bang, and the size about 250 parsecs. So I just want to show you the data of this. So this is showing you the spectrum of this galaxy. So again, a very nice break. And you can see that this galaxy has a bright neighbor. So you might say, well, this is very worrisome, Sandro. But actually, we took spectra of both systems. And you can see in orange, that's basically a foreground galaxy. And you can clearly see that this galaxy lies at redshift 3.47, thanks to the Balmer break. But then the high redshift galaxy, the Lyman break, is clearly offset. And so we basically confirm now the first galaxy above redshift 14. And the papers have been on the archive since yesterday, so you can look at them more. I think they are very surprised. I mean, this object in particular is surprisingly bright, has a UV magnitude basically of minus 20.8. And it's quite red in the sense of like the beta slope is about minus 2.2. And so we still try to make sense of all this. But overall, it seems that the absence of emission lines in this system can be used to infer, for example, an escape fraction, which seems to be rather high. So there's a lot of data modeling that is still ongoing, I would say, but this object, I think, is very interesting. What it makes it even more strange is that it's actually detected in MIRI. So down here, I show you the MIRI data. Oh, sorry, the pointer. So here is the MIRI data. And you can see that the SED point is very high, which we think is because oxygen 3 and H beta are contributing there. And of course, we would like to disentangle whether it's oxygen 3 or H beta because the differences in the interpretation are quite large. But the idea, and again, the indication because of the rather red UV slope together with the MIRI detection, we think that there is clear indication for dust attenuation in this system. So again, this indicates that this system must have gone several bursts of star formation before being as bright as it is now. Okay, so by this, I think I'm ending. I'm just show you this movie basically, which is kind of a zoom in onto the system. What you can see again is basically, we were quite lucky to find this system, I think, because again, it's blended with a foreground galaxy, and it took us you know, kind of a lot of deblending skills to deblend these two systems and then really do the spectroscopic follow-up of the background galaxy. And so with this, I'm ending here, and thank you very much for your attention.
Thanks very much, Sandro. How long was the exposure time for the spectroscope, for the NIRSpec?
So, well, for the imaging, actually, it was 50 hours per medium band. So it's very deep. It's the deepest images we have taken. With NIRSpec, I think I have to see the exact exposure time for this object, but it was also of the tens of hours, I think. Now, for this object, we wouldn't need that much time probably because it's so bright. But we had other objects, you know, where we couldn't detect anything. So we probably have to go even deeper.
Okay. So, sorry for holding up the first questions. Are there any in the audience? Marta.
So thank you very much. It's really amazing. So one comment first about the black hole masses compared to the galaxy masses. So the same bias that you discussed about the bursty star formation acts exactly in the same way on the black hole. So we working on AGN have been expecting to see overmassive black holes. So I would be careful about biases. The other question I have is, so you showed several star formation histories. And I've always been curious to understand how much the priors influence the results, mainly because I've seen some results change over some galaxies. And so I'm a theorist, so for me, it's very difficult to understand this.
Yes. So regarding the priors, I think that indeed that's something that is, I think, still underexplored. So we have written just a few months ago a paper that we introduced another prior, a new prior, for understanding better the burstiness of star formation, because the priors that a lot of the people have been using in the past is based on actually illustrious TNG or illustrious models, where you basically look at what is actually, because you say non-parametric star formation history, which just means we have bins of star formation, and you still need to define what the covariance is from bin to bin. And there, basically, you have been usually tuned this to something like illustrious, which is quite smooth. And so with HST modeling, I already changed that and implemented something that is more bursty. But now also with the more flexible power spectrum approach that I showed you before, we actually implemented this in the SED modeling as well. So again, I think these are at the moment, I mean, there's a fundamental limitation that if a galaxy is undergoing a burst, that you just don't see the older stars. And so that's just important that you run different priors and see how actually the results change. Now with the Bayesian way, it's kind of efficient to do this, and you can then look, for example, did your prior really shrink? By how much? Like so going from prior to posterior distribution, do you really shrink it? So that's a way to do it. I think the future, one thing that we are developing now is what we call like Bayesian hierarchical models, where you say, well, you try to fit for these prior parameters as well, like for example, for the burstiness, right? So you basically fit all these galaxies, but you still have something like the burstiness that is maybe common among all the systems. The exact shape of the star formation histories are different, but the variability spectrum might be the same or similar. And so you can try to model this at the same time as well. So yeah, there are ideas of how to overcome that, but generally speaking, there is a fundamental limitation. And so I think you can only learn really from about it if you include information from several systems. So for example, seeing how many actually going through a burst versus not burst, and do the analysis then on all of them simultaneously.
Thanks. Hi, I was wondering, with the new data coming in, is there any change happening to the redshift versus types of galaxy, in general, the tuning fork diagram?
Yes, I mean, well, so again, it depends how we define the types of galaxies, right? So I mean, I think that in particular, when we go to earlier and earlier times, galaxies are indeed much more compact. And I think that's also, we need different analysis tools. And I think that also the timescales over which they vary the star formation is on shorter timescales. Now, we still need to observationally show that, but there are clear indications for this. And so I think that is important then for the interpretations we just discussed, for example, for the SEDs, but also actually for the biases, okay? Because again, there are I think a lot of biases that are underexplored and still need to be fully incorporated. Again, we are usually finding the things that are undergoing a burst much easier than the ones that are not. And for the black holes, again, we are finding certain galaxy, objects that are undergoing accretion, for example, more actively, right? And so understanding like what underlying distribution of the properties like black hole masses is much more uncertain. Yeah.
Yes, I was wondering about the galaxy GN-Z11. You mentioned you have an extended disk, and I was wondering about the size of it. And I was also thinking that you mentioned the importance of this mini quenching and this bursty starburst. Then yes, the importance of minor merging all along the history of the universe must have been or must be very important. Is that right?
Yes. So, well, the size of this disk is only a few hundred parsecs. Okay, so we're not talking of like a large scale disk. But again, these systems are overall very compact. So it's consistent with the idea that the systems are basically a few hundred parsecs in size. We do also more statistical analysis on like the size-mass relation, for example, and there is a significant scatter there, but typically galaxies are well below a kiloparsec. And that's why I think the challenge is really the PSF, is off the order of that size. So you start hitting basically. So what we do is we do a lot of tests with brown dwarfs because we have actually a lot of brown dwarfs that seem to be like high redshift galaxies. But we are understanding exactly what our resolution limit basically is. How well can we say something, whether it's a point source or whether it's spatially resolved. The other question about minor mergers, yes. So again, the galaxies we are probing now, on a daily basis, like 10 to the 8 solar masses. And some of them show substructure. So there seem to be multiple components there. So like the object that I showed you with the clump, it's actually quite difficult to say whether this clump is a minor merger or whether it's even a disk instability. Now it's rather bright, but still, if you fit the SED with it, you get a low, away with a 10 to the 6 solar mass system. So I would say that it's probably a minor merger, but it's actually quite difficult sometimes to disentangle. Are these clumps, actually smaller galaxies that came in, or were they forming as part of an interaction, or are they kind of disk instabilities? And so I think we're similar like at redshift 2 when we had all these clumpy galaxies, and we're still, I think, in the regime to understand, what is actually the ages of those clumps? Is there any radial variation? Are these clumps that are, migrating in? So I think we have very similar questions at high redshift, but I think also a lot of us who are working there now will go back to redshift 2 and try to address these things now because we have, Paschen line observations which help with the dust attenuation, for example. Yeah.
Thanks, Sandro. That was marvelous. I have 2 questions. One, you can set a lower limit to the cosmic star formation rate. Of course, as you said, you have biases against seeing old populations and maybe smooth star formation populations. So, do you see the continuation of the Madao plot, or is it higher or lower?
Yes. For
your lower limit.
Yeah, I skipped.
Maybe I missed it. But,
yeah. No, I skipped also that. What the results show? Well, in the literature, I think typically we are still below the Madao, and this is a figure that I'm working on, so it's horrible. But basically, what it shows you is. I don't know, can I? Oh yeah, here, sorry. So again, this is showing the cosmic star formation density. This is redshift.
Yes.
And so the Madao plot would be kind of up here, okay? So we are still below it, but we are, this orange line shows you this halo model that I showed you before, which is this strong decrease. And you can see that more and more data is coming in that is basically clearly above this line. So we are somewhere in between.
Yes.
And so that's why this motivates the question about whether star formation was probably more efficient than what we would have expected from these simple models. But one of the things that is difficult to, understand, which is actually, typically we use the UV luminosity to measure the star formation rate, but even the UV, right, probes kind of a range of ages. And so if these galaxies are actually undergoing very intense bursts, it might still be that the amount of stars that are formed actually quite low. So the star formation rate might be actually lower than what we would simply use when we use a simple Kennicott-like conversion factor.
Yes, thank you.
Yeah.
So my second question has to do with morphologies.
Yes.
Now, of course, at redshift 9, you have 10 magnitudes of cosmological dimming. And if galaxies today have surface brightnesses of, let's say, 24 magnitudes per square arc second, I guess that's beyond the reach of JWST unless you do very, very long programs. I don't know how far you go in the surface brightness. But if you stop at redshift 6, 7, you can, my question is, can you start seeing objects that look like ellipticals?
So again, I don't think that we have many of these very massive systems. When you think about look like ellipticals, again, I think when we go to redshift 7, we found this object, for example, many of these objects are actually very small in size, but still have 10 to the 8, 10 to the 9 solar masses. So if you just do, a quick calculation what the stellar density is, stellar mass density, you come back and tell me like that's actually very similar to what we find in elliptical galaxies. So it seems that the cores are at least present in some form. Now, of course, you can see
like the example you showed.
There's maybe exactly. There's still some change that can happen to that, right? You can have adiabatic expansion and so on, and fresh gas coming in, forming additional stars. Regarding the surface brightness dimming, I think that's some of the things that we're heavily, look into, because again, what it shows up there is basically the intrinsic size. Now, again, this shows you in arc seconds as a function of the luminosity, and we show you basically completeness. And so indeed, we start losing objects that are of the order of about an arc second in size. Okay, now this is specifically for looking at the redshift of 8 and above galaxies, but we try to do similar things when we learn about the size-mass relation, because one thing that we are finding, and I can show you a diagram that looks like this, when you look at the rest frame optical sizes at redshift 6, okay, so this is size or log size, that's it, this is just size, this is 1 kiloparsec, this is 0.1, and this is 8, and this is 9, and this is 10 stellar masses. You find something that, yes, so there are galaxies like this, but then they are dropping quite significantly below 10 to the 8, going down to 10 to the 7. So there is a very strong decrease when you would just have a simple linear relation in log space. Like there seems to be a strong decrease. And we are wondering now whether this is because we're missing those objects. So we're running these kind of source injection, codes to basically try to understand that. One thing that we clearly know is that we don't have very compact systems here at 10 to the 9.
It might be that the most compact ones are having gas flows inside, which are making bursty star formations, so you see them.
Exactly.
Yeah, so this might be your little dots, your little...
Exactly. So we are trying to understand exactly this completeness, both the biases in mass. The mass completeness drops towards 10 to the 7, but we are still, I would say, 90% complete. I mean, yeah, in those surveys, down to 10 to the 7.5. Okay, so we are complete down to the 7.8 in mass, but then below 10 to the 7.5, it's getting more difficult. Yeah, and we are biased.
So I thought the starburst aspects that you're finding are just seem ubiquitous, very interesting. What can you hope to say about the duty cycle eventually, and whether that could even vary with redshift? Is that something you could eventually extract?
Yes, so the duty cycle of star formation, you mean?
Yes.
Yes, so if I look at the data we have at the moment, now I didn't do very careful estimates, but if I look at the different spectra that we have for hundreds of galaxies and try to see how many galaxies are in burst phase versus quiescent phase versus in the cluster rejuvenation phase, because we can find objects that have the DN 4000 break, but also emission lines on top. It seems like they're just coming back up. Then I would say that the timescales of the order about 20 million years. Okay, so plus minus 10 million years. But that's the roughly timescale for these oscillations at 10 to the 8 solar masses at redshift 7, basically.
And presumably that could vary with redshift too. You might expect a higher frequency.
I would not be surprised at all if that's the case, yes.
And finally, does the redshift 14 object have an AGN or black hole?
So we looked at the spectrum, and the spectrum doesn't show any indication for that. I think the main thing that speaks against it is actually morphology. The galaxy has a size of about 300 parsec. So it's actually very large, and if it's HN dominated, it would be clearly as a point source, at least have a point source contribution. But we don't find anything in the imaging. So that speaks against the HN solution.
Plans on following up with the MRS spectroscopy, near spectroscopy?
Yes, we put in the DGT yesterday.
Okay.
Yes.
Thank you again for the presentation. I guess I'm sort of following up of some of the questions you've had already. Most of the models you presented are very much spherical collapse based, whereas star formation we know is dependent on the morphology and the way the gas is being accreted onto the objects. So do you intend to, because you didn't even mention once angular momentum, I think, in your presentation. So how would you comment on that?
Yes, that's actually, I have actually slides, or at least another presentation, but I already had to, dense it down to this basically. But indeed, there is I mean, I myself have been looking into cosmological zoom-in simulation. And one of the things, that we focused on is redshift 1 to 6 and understand the variation of star formation and the formation of bulges. And one of the things was indeed, the key thing was that because these galaxies are gas rich, that you can actually, don't need necessarily a minor merge, but even a counter-rotating stream of gas that lowers the angular momentum of the gas disk, and you fuel a lot of gas into the center of the galaxy, forming a bulge-like component. So these are things that I think are ongoing there, but it's something that I didn't have time to really cover, unfortunately, in my talk. But I think it is indeed very important. I think at the moment, we are still very much just focusing on measuring the basic stellar population parameters. Now we're slowly moving into the morphology. And hopefully then we can learn more about, for example, what the diversity of sizes are at fixed stellar mass and redshift to basically say something about, for example, is this similar to what we expect for the angular momentum distribution of the accreting gas?
Thank you.
We'll take one last question online by Michel. Michel, the
yes,
mic.
yeah. I have a question about the emission lines you saw in some of the galaxies. If you can come back to the first one you showed at Z equals 7.4, please.
Yes?
Yeah, in the spectrum, I was puzzled by the fact that you see quite a strong neon tree line at 3870, which is very hard to produce with such a strength compared to H beta, unless you have very high energy photons. So probably this means that you have an AGN in that object. Yet in the high redshift objects, you have not seen these neon tree lines in any of those where you claim there is an AGN. So does that mean that the AGN is completely hidden in central dust or something like that?
So that's a very good question. We looked into this. We can get away with producing those lines, at least in some cases, and in this case, I think with just binary models and very young stars. For GNC11, we see we see some of these neon lines as well, actually. So so I think that's I'm sorry, where is that?
Yes.
Yes. Well.
Yeah, I didn't see it on this one, but
yes. So anyway, but I think overall it's a very important question, I think. So again, I think when we look at some of these diagrams, I mean the BBT diagram from redshift 0, but even more complex diagrams, what we find is that because we are entering this very low metallicity regime at high redshift, we are starting to see that basically these HEN and these star formation models start more and more to overlap. So it starts to be much more difficult to use some of these emission lines to actually, say for sure whether it's either or.
Oh yeah, okay. Thank you very much. Yeah.
If there are any other questions, let's thank Sandro again. Thank you.
Thank you. Sorry, I was running out.